Ok, stiamo registrando. Ok, vedete le slide a casa?
Sì.
Okay. So let's start. So yesterday we started our journey into the internal structure of the proton, and we started with the low energy phenomena, so essentially elastic electron proton scattering. The electron is the ideal probe to study the electric charge distribution and also magnetic moment distribution inside the proton. And we discussed several approximations that we removed step by step, and at the end we derived a more general form of the cross-section that also takes into account the spatial distribution, indeed, of the electric charge and the magnetic moment in terms of the electric and magnetic form factors. So let's now continue this journey now by increasing energy, and so by moving from elastic to inelastic and deep inelastic regime. So still a few words about the elastic regime. So in elastic electron-neutron scattering, it is a powerful tool to study the macroscopic properties of the nucleon, okay, such as the Hermes radius, as we have seen yesterday, and the spatial distribution of the electric charge and of magnetic moment through the indeed electric and magnetic form factors. Now, as we also seen yesterday, the elastic scattering cross-section decreases quite rapidly with energy or transverse momentum, and inelastic processes become more and more probable at higher energies. So in an intermediate regime, so at moderate center of mass energy, the electron-neutron inelastic scattering can cause the proton excitation. So in which sense? So you see here now the process. So we have an incoming electron that scatters off a proton through the exchange of one single virtual photon. This is our proton in the initial state, and in the final state, our proton becomes excited in this inelastic process. Or in other words, it is transformed into one of the so-called nuclear resonances, so the delta resonances, which belong to the 3½ minus baryonic decuplet, as we studied already. So let me show you now some experimental results. Okay, so this is indeed the differential cross-section for inelastic electron-proton scattering over a certain range in the energy of the scattered lepton, E3, or equivalently in a certain range of the W variable, which describes the invariant mass of the hadronic final state. In particular, these data have been collected with a magnetic spectrometer by measuring the energy of the scattered electron at a certain angle, theta 10 degrees, and using a beam energy of 4.9 GeV. So here, as you can see, we observe a lot of structures. First of all, at the highest energy of the scattered lepton, we observe a huge peak of elastic scattering. This is damped by a factor of 15, so this is actually 15 times taller than this. Then, as soon as we move now to smaller and smaller energies of the scattered lepton, the remainder energy is, of course, gone to the proton, which indeed can become excited. And in fact, here we observe structures, okay, which corresponds to excited states of the nucleon, so the delta resonances I was mentioning before. So let's discuss them one by one. So the first peak here, indeed, is the elastic peak. It is at 4.5 GeV, and this corresponds to an invariant mass of the hadronic final state just equal to the proton. So the proton remains intact and in the ground state. Now, for lower energy electrons, we observe here a big peak, a huge resonance, indeed, which is the delta plus baryon that we already studied. Is a member of the isospin quadruplet in the baryonic decuplet, with a mass of 1,132 MeV. Okay, and then this we studied already that it decays strongly in a proton pion with a decay time of the order 10 to the minus 24. Okay, so this is a typical hadronic resonance. Then, moving still to lower and lower energy, we observe other structures which corresponds at a certain energy of the electron. We see the values, which corresponds to the production of other, even heavier nucleon resonances. And then finally, okay, when we move down to W greater than 2, okay, so in this region here, we reach a continuum. Okay, so we don't excite any more resonance states, but we now reach the continuum, and this is indeed the regime of the deep inelastic scattering, as we will study better today. Now, in the elastic or inelastic scattering, the invariant mass of the hadronic final state, so the W variable, coincides either with the proton mass in case of elastic scattering, or with the mass of the nucleon resonance in case of inelastic scattering. Okay, so it just takes one value, essentially, with a certain distribution. And the process is only requires one kinematical variable. So it is the kinematic of the process is fully described by just fixing one single kinematic variable. So, for instance, if you fix the angle theta, then you get you also fix automatically the Q square and the outgoing energy of the electron. Okay. What about now deep inelastic scattering? Okay. So deep inelastic scattering is a quite different process, because now, as you can see here in the picture, the proton gets a huge burst of energy from the incoming electron through the exchange of a large momentum virtual photon, and it breaks up. So we don't observe anymore the proton in the final state, but a bunch of typically undetected hadrons. Okay, this can be pions, kaons, whatever. Okay, typically in this kind of measurements, one only measure and detect only the scattered electron, and it is sufficient to gain information about the structure of the proton, as we will see today. Okay, these are called inclusive measurements. Okay, because you allow for any possible hadronic final state. As we will see next week, there are also more complex measurements, which are, for instance, semi-inclusive, where you actually detect one of the final state hadron in coincidence with the scattered electron. But this we will see next week. Okay. So now we have in the final state a bunch of hadrons, which derives from the breakup of the original proton. And the W value, actually W square, actually is not anymore a single value, but it can have a distribution of value, because it depends also on the form momentum provided by the virtual photon. So W square, which is the form momentum P4 of the final state, is actually the sum of the form momentum of the incoming proton and the form momentum transferred to the proton by the virtual photon, or by the electron through the virtual photon, if you like. And this can only be equal in the limit case of elastic scatter, or greater than the mass of the proton in the general inelastic case. Okay. And in addition to that, in the deep inelastic scattering, in order to describe the full event, one needs two independent kinematic variables, okay, which have to be Lorentz invariant. So only one in case of elastic inelastic, but you need two in the case of deep inelastic processes. So which variables can we use for our description to describe the event and the process? One of those Lorentz invariant variable we already encountered yesterday. It is the negative form momentum squared of the virtual photon. Okay. Yesterday we derived a Q square, which is a negative quantity because it is a T channel, but then we redefine this as a positive quantity with the capital Q square. So this is one possibility, one possible Lorentz invariant kinematic variable. Another very important variable that is typically used to describe the physics of deep inelastic scattering is the so-called Bjorken X variable, okay, which is defined in this way. So this combination of four momenta, and it turns out that it is limited from 0 to 1, okay? So I cannot get a value larger than 1. So what is now the meaning of this variable? Let me reply only partially now to this question, and we will come back to this later today. So one first interpretation of the physical meaning of the X Bjorken is the following. So suppose that your proton is at rest. So the form momentum P2 of the incoming proton is just the mass of the proton. Okay. Now let's develop the W square, okay, which is the square of P2 plus Q, as we've seen in the previous slide. And so we have here the expansion of this square, okay? Now, Q square we can rewrite as minus capital Q square, as we have seen here. Then we have the double product, and then since we are with the proton at rest, P2 is just the mass of the proton squared, okay? And as we have seen, for the case of deep inelastic scattering, and in general, in the case of deep inelastic scattering, this must be greater or equal than the mass of the proton, okay? Now, let's come back to our definition of the X Bjorken. And let's take the limit where X is equal to 1. Of course, X is equal to 1 when the numerator is equal to the denominator. Okay, so when Q squared is equal to 2P2 times Q, which is indeed this part in red. So if this happens, so if we are sitting in this limit value of X, then this part in red drops, okay? Of course, this is just identically 0 in this limit, and the W square corresponds to the square mass of the proton. So we are back to the elastic case, right? This corresponds, let me go back again here, to the situation where we have this elastic peak, okay? Where W corresponds to the mass of the proton. So in other words, okay, one first interpretation of this Bjorken variable is that it quantifies the level of elasticity of the scattering process, okay? The closer to 1, the more elastic the process is. On the other hand, very small values of X, as we will also see later, corresponds to, indeed, the deep inelastic regime. Now, we have also other two possible variables that we can use for describing our process, which are the nu and the y, which are given by these two combinations of four momenta. Now, given this form, they don't tell us much, but if we now represent them in the proton rest frame, then their meaning is quite simple. So the mu corresponds to the energy lost by the electron. So the initial energy minus the final energy. What is lost is what is transferred to the proton through the little photon. And y is just nu divided by E1. So it is the fractional energy that is lost by the electron. Okay. So in this particular frame where the proton is at rest, the physical meaning of these two variables is quite clear and straightforward. Of course, these two variables are not independent, as you can see here. Okay. So one cannot choose both of them to describe the process. And so in fixed, for a fixed center of mass energy, the kinematic for the deep inelastic scattering can be described by any pair of these two variables, these four variables, Q square, X Bjorken, Y, and nu, except for the Y nu pair, which indeed is not an independent pair. Okay? And typically, one uses the X and Q square variables to describe the process. This is the most common choice. So let's now see indeed the cross-section as a function differential in X and Q square. Okay. So what you see here is the most general Lorentz invariant differential cross-section for electron-proton scattering mediated by the exchange of one single photon in the DIS regime, so where the Q square is much larger than 1 dV squared. So what do we recognize here? First of all, we have two new objects, which are capital F1 and capital F2, okay, which are called structure functions. These are the structure functions of the proton or of the nucleon in general. In particular, F1 is a purely magnetic structure function, and F2 is electromagnetic structure function. So it has both electric and magnetic contributions. And as you can already imagine, the structure function in deep inelastic scattering essentially play the same role played by the form factors in elastic cross-section, in elastic processes. Okay. So essentially, they embed all the information about the internal structure of the proton. Okay, all the rest is just pure QED. Okay, the information, the physics, the dynamics inside the proton is encoded in these two objects, F1 and F2. Okay, and how can we measure this? So these two structure functions can be measured through the measurement of the DIS cross-section at fixed value of x and q squared, but at different values of the beam energy, much like the similar procedure that is used for measuring the form factors in elastic scattering, as we have seen yesterday. Now, let's now go to some historical perspective. So the first studies, let me actually go even back. So we discussed in our QCD chapter that there were been many attempts to detect free quarks, okay, with different beams, with different energies everywhere, and all these measurements failed because, as we know now from QCD, from confinement hypothesis, free quarks cannot exist because they carry color, okay. So the quark model by Gell-Mann and Zweig was very elegant, but still needed to be proved experimentally. Okay, and the direct search of quark was just a total failure. So the experimental way that quarks have been finally discovered and that their existence have been finally proved and established is indeed through deep inelastic scattering, as we will see today. Okay. So the first studies of the structure functions in deep inelastic electron-proton scattering were performed at SLAC in California at the end of the 60s. So I think it was 69 or 68, 69. So they used an electron beam with energy in the range from 5 to 20 GeV, a liquid hydrogen target, so essentially proton target, and a large movable magnetic spectrometer that they needed to detect the scattered electron. Okay, so back to here. So they were moving the spectrometer, okay, so they were changing this angle such to detect these scattered electrons at different angles. And they found very, let's say, unexpected results. Well, maybe expected, okay, but really striking. So the first kind of result that they found is that the two structure functions, F1 and F2, are almost Q-square independent. Okay, so if you see here in these very first data from SLAC, when you plot F2 as a function of Q-square, the distribution is flat. Okay, there is essentially no or only little Q-square dependence, and this phenomenon is known as the Bjorken scaling. So in first approximation, but according to the first data from SLAC, one can even drop the Q-square dependence and just write down the structure function as a function of the x Bjorken variable only. And this was the first interesting result. So what is now the physical interpretation of this Bjorken scaling? So as I was mentioning before, the two structure functions in DIS take the same role of the form factors in elastic scattering. And as we've seen yesterday, one can obtain the charge distribution of the proton by the inverse Fourier transform of the form factor. Okay, so we can in principle use the same idea here to draw some physics from this Bjorken scaling. So if our Q-square dependence is flat, okay, and then we virtually calculate the inverse Fourier transform, then what we obtain is a point-like distribution. Okay. And so the lack of the Q-square dependence of the structure function suggested for the first time that the DIS scattering is occurring not from the proton as a whole, but really from point-like constituents inside the proton. So this was the very first experimental indication of the existence of quarks inside the proton. The second very important result that they obtained is the following. So suppose now that these point-like objects inside the proton are fermions, in particular spin-1/2 fermions. Then in this hypothesis, one can show that the F1 and F2 structure functions are not independent, but they are related by this relation, which is known as the Callan-Gross relation. Okay, so essentially through the x Bjorken variable. Okay, so if you find this relation fulfilled in your data, then this is a proof that your point-like object that you are probing are spin-1/2 fermions. indeed, as one would expect for the quark hypothesis. And this is, in fact, what they found. So you see here now the ratio 2x F1 divided by F2, and this ratio is indeed consistent with 1, okay, within the experimental uncertainty. So the Collinear relation, which was just predicted before that, assuming that a point-like object in the proton were spin 1 fermions, it is indeed fulfilled. Okay. In particular, if this point-like object were a spin 0 object, okay, then the magnetic structure function would be 0, of course, because there is no magnetic moment, and this Collinear relation will be, of course, not fulfilled by data. So we can now put the two results together, okay, and draw some fundamental conclusion. So these two relevant observations can be interpreted by assuming that the underlying process in electron-proton deep inelastic scattering is the elastic scattering of electrons from charged point-like spin 1/2 particles within the proton, indeed the quarks. Okay. So this is indeed the very first and clear experimental evidence of the existence of quarks. Why charged? Because, of course, this is an electromagnetic process. So you can only interact with charged objects. Okay? And in particular, the results could be only interpreted correctly if one assumes a fractional charge for the quarks. Okay? So from deep inelastic scattering, we get a lot of information about these objects inside the proton. They have to be point-like. They have to carry a fractional charge. They have to be spin 1/2 fermions. Now, there is a very important model that was developed in the 60s by Feynman and also Bjorken, which allows to indeed interpret what is going on in deep inelastic scattering phenomena processes. This is the famous Proton model, okay? So let's now illustrate what this model is about. So according to this Proton model, the basic interaction in deep inelastic scattering, electron-proton scattering, is indeed the elastic scattering from the electron and spin 1/2 point-like object inside the proton that they called partons at that time. At that time, they didn't even call them quarks, although the quark hypothesis was already there in the market. They just call them partons, okay? So suppose we have a point-like spin 1/2 partons inside the proton, then the deep inelastic scattering, so the high energy scattering of electron on a proton target, can be interpreted as elastic scattering of the electron with single partons, inside the proton. The model is based on a very reasonable approximation, which is called the impulse approximation. So it is assumed that the duration of the photon-parton interaction is so short and so intense that during the scattering process, one can completely neglect the interaction among the other quarks. Okay, so in other words, the interaction is so short in time and so intense that one can assume that during the scattering process, quarks are not interacting between themselves. We can neglect any interaction between quarks. And so, essentially, we can assume that they are quasi-free inside the proton. And so, once more, overall, the deep inelastic electron-proton scattering is interpreted in the Proton model as the incoherent sum of scattering processes of the beam electrons with the individual partons, where incoherent means that we just have to add them without any interaction among them. It's like you're interacting your beam of electrons with a bunch of non-interacting partons. Okay. Now let's look into the process in more detail. Okay, so clearly it is an electromagnetic process that at fundamental level occurs between the electron and the quark. Okay, so it is essentially just like the molar scattering, where instead of having electron-electron scattering, we have electron-quark scattering. Apart from that, everything is just described by the molar process. And you see here the process also depicted in the center of mass frame. So you have your colliding electron, your colliding quark, okay? And then you observe your scattered electron at a certain angle in the center of mass frame. And in the center of mass frame, of course, the total momentum in the initial state and the final state must be zero, so the momenta have to be opposite, and we just can call them pi for the initial state or pi for the final state, okay, in magnitude. And in magnitude, this has to be order of half of the center of mass energy each, okay? Now, we have now all the instruments to compute the matrix element for this process. Indeed, it is just exactly as the molar scattering, with the only difference that here we have to take into account the fractional charge of the quark at the bottom vertex, okay? So the upper vertex and the propagator are just the same as the molar, and for the lower vertex, we just have to take into account that the quark carry only fractional electric charge that we call Q2, okay? And so we can write down now, we can also divide by minus I, we can obtain our transition matrix element in this way, okay? Now, as we have seen already in QED, we can calculate now the average squared, the spin average squared matrix element, okay? Which can be expressed in terms of the Mandelstam variables that you see here for reference. Now, we realize that this is a T-channel process, so the T corresponds to the Q square of the process, and so we can just substitute the T square with the Q to the 4 here. Now, once we have this quantity in hand, we can put it inside the formula for the cross-section, okay? And so we can obtain our differential cross-section in this way. So this is the general formula that we derived from the Fermi golden rule, and we now substitute the previous expression of the spin average squared matrix element, okay? And we recall this relation here. So this is what we obtain. Now, with some algebra, okay, that I don't care about, but if you are curious, you can find in the textbook, then one can rewrite these in a different way and more useful way, okay? So this is at the end your differential cross-section or differential with respect to Q square. And why is this shape more useful? Because you can now compare these with the one that I provided you before, which is the most general Lorentz invariant cross-section for deep inelastic scattering. If you now compare the two, okay, you see that apart from the fractional charge here, you see that the structure of these two cross-sections is indeed the same, and the only and main difference is that now at the quark level, so the elementary level, of course, the F1 and F2 structure function are equal to 1, because clearly at the elementary level they describe structureless objects, okay? So when you look at the proton as a whole, they describe the internal structure of the proton in terms of electric and magnetic distribution. When you look at the elementary cross-section, electron-quark, they are just one because both electrons and quarks are, of course, structureless objects, just point-like. Okay. Now, still in the Parton model, the interpretation of the deep inelastic scattering is considerably simplified with a suitable choice of the reference frame. Of course, the physics of the problem is independent of this choice. So, the Parton model is indeed formulated in a frame where the proton has very high momentum. This is called the infinite momentum frame. So suppose that your proton is not at rest, but it is traveling along the z direction with the infinite momentum, okay? And then you sit your frame into this proton. So in this frame, the proton mass and any transverse component of the momentum, so along x and along y, can be neglected. For infinite momentum, of course, you can neglect the mass, okay? And since everything is longitudinal, so it's along the z direction, you can neglect in a very good approximation all the transverse component of the momentum. So px and py can be set to 0, okay, in this frame. And so we can write down now the 4 momentum of the proton in this infinite momentum frame. So in general, it is given by these 4 components, but now in this frame, essentially the transverse component of the momentum are just 0, okay? And the Z component of the momentum corresponds to the total energy, because we are neglecting the mass, okay? So this is the way we can represent the form momentum of the proton in this infinite momentum frame, and so essentially in the Parton model. Now, in this frame, again, we have to consider the proton as a composite object with quarks inside, or partons better inside, okay? And since the proton is moving with the infinite momentum along Z, okay, for the same reason, we can neglect all the transverse component of the quarks momentum, okay, and also, of course, the quark masses. So we can imagine the proton as a bunch of quarks that are all moving longitudinally along Z with infinite momentum. So we can neglect any transverse component of the motion. And this approximation is called the collinear approximation. We will come back to this tomorrow, next time. So once more, in the collinear approximation, the structure of the proton depends only on the longitudinal, so along Z, component of the parton's momentum. And therefore, the form momentum of partons can be written as a fraction Xi of that of the proton. So the proton is a bunch of collinear quarks. The proton has a total form momentum P2, and so each quark carry a fraction of this longitudinal form momentum of the proton. Okay, and you see it depicted here. So this is our proton moving with E2 P2. Okay, and so each constituent of the proton in this collinear approximation, where one neglects all the transverse motion, carry a fraction C of the energy and the form momentum. Okay. And so in this picture, what happened during the scattering process? That the virtual photon interact with the one of the quarks. Okay. The virtual photon carry a form momentum Q. Each quark carry a form momentum psi P2, so a fraction psi of the total momentum P2 of the proton. And so in the final state, the form momentum of the quark, of the scattered quark, would be psi P2 plus Q. So let's now make use of these to derive on the blackboard a very fundamental result of the Parton model. So in the infinite momentum frame, where we have the form momentum of the proton, which we call P2, is just P2, 0, 0, P2. And the form momentum carried by each parton, okay, or each quark, if you like, P2i, is just a fraction of this, of P2. And so this is psi P2, 0, 0, psi P2. So this is before the scattering. In the scattering process, the quark is hit by the photon, so it gains more form momentum. Actually, the photon transfer to the quark is form momentum Q. So this is initial I. After, or the final, after the scattering, this is increased by quantity Q. So this is the quark initial form momentum plus Q, which is the form momentum transferred by the virtual photon in the process. And so this is psi P2 plus Q. Okay, as it is written in the bottom part of the slide. Now, let's take the square of this. Or it's going to be psi P2 plus Q. And so this is psi squared P2 squared plus 2 psi P2 power Q plus Q squared. And then, remember from our first lesson, from the mass shell relation, this must be equal to the squared mass of our quark. Okay, P2 P squared is equal to m squared, mass shell relation. Okay. So now let's make some consideration. First of all, we are working in the DIS regime. DIS regime is a high energy regime, okay, where the transverse Q squared is generally much greater than 1 in V squared. Okay. And the mass of the quark, we are talking about up and down quarks essentially, is order over Q and EV. Right? So with very good approximation, we can neglect this quantity here, and it is essentially equal to 0 in the DIS regime. Furthermore, inside the proton, there are many quarks, not just 3, okay, as you know. And so this fraction here, in general, this fraction here, okay, depending, of course, on your resolution, as we will see later, but it is in general a small number. It's a fraction of 1, it's a small fraction of 1. And so when you take it square, is it an even smaller number. So this is also negligible. And so here we obtain that 2 psi P2 star Q plus Q squared essentially is equal to 0. A very good approximation. And then we can derive now C here. Yes, which is minus Q squared divided by 2 P2 star Q. Or, if you like, capital Q squared divided by 2 P2 star Q. What is this? Can you recognize this object?
It's the X-Bjorken.
X-Bjorken, indeed. And this is the measure result. This is our X-Bjorken variable that we defined before. So what is now the message? The message is that in the Proton model, and so in the infinite momentum frame, the X-Bjorken variable that we introduced before as a measure of the elasticity of the process actually corresponds to the fraction of the momentum carried by each parton. Of course, this is not true everywhere, but this works in this reference frame. And so this is indeed what comes out in the framework of the Proton model. Okay? So the X-Bjorken variable can be actually interpreted in the Proton model as the fraction of the momentum carried by each quark, by each part. So let me stress this again on the slide because it's a very important result with important consequences. Okay. So in the infinite momentum frame, the Bjorken X variable can be identified with the fraction of the momentum of the proton carried by the parton or by the struck quark. Okay. And so the measurement of the X dependence of the structure functions, if you remember, fractional function depends on X and also on Q squared, but essentially on X due to the Bjorken scaling. So the X dependence of the structure functions can then be related to the momentum distribution of the partons within the proton. This is the fundamental point. Okay. And these distributions are expressed in terms of the so-called parton distribution functions, or PDFs. So what is a PDF? For example, the up quark PDF into the proton that we can denote in this way as a UPX, U for up quark, P proton, X Bjorken. It is defined such that this quantity multiplied by the X represents the number of up quarks within the proton with the momentum fraction between X and X plus the X. Okay? So the PDF, when you multiply your PDF for a certain quark flavor with the X, this gives you the number of quarks inside the proton which have a fractional momentum in this range from X, X plus the X. Similarly, one can define the down quark PDF, okay, the DPX, and again, this represents the number of down quarks within the proton with a momentum fraction between X and X plus the X. Now, PDFs are non-perturbative objects, okay, in the sense of QCD, non-perturbative QCD, so they cannot be calculated from the QCD Lagrangian or from first principles. So they need to be essentially measured experimentally. Okay. Other possibilities, as we studied last week, is that one can also use a lattice QCD, okay, to calculate this object on the discrete lattice. And there are indeed now quite recent and also interesting results from the lattice QCD. But the main approach is to measure experimentally these objects because they cannot be predicted from the QCD, from the theory itself, from first principles. Now, in the most simplest picture of the proton is made up by 2 up quark and 1 down quark. So essentially by 3 quark, okay? So suppose now, to make things even easier, so suppose that these 3 quarks are not interacting with each other, okay? So they have just three free particles inside the proton. Then in this case, each quark, of course, carries a fraction of 1/3 of the total momentum of the proton, okay? The total momentum as a fraction of 1, we have 3 quarks that are not interacting, so each share 1/3 of the total longitudinal momentum of the proton. And so your quark PDF that you see here, okay, QPX, is just a delta Dirac centered at 1/3. Suppose now that we still have only 3 quarks, but now they are interacting, so they exchange gluons, as we know from QCD, okay? Now, in this case, the delta function at X 1/3 is mirrored due to the momentum exchange among quarks through gluon exchange. So let's say the maximum is still around 1/3, okay? But now it is not anymore a delta, but it is now smeared due to this momentum exchange through gluon exchange. Of course, as you know, the proton is not such a simple object. It is a much more complex system. Quarks not only interact with each other through gluon exchange, but as you know, gluon can also split into Q-Cuber pairs. And Q-Cuber and the quark and antiquark that are created can radiate new gluons, which can further split, and so on. So indeed, the QCD vacuum is a mess of infinite gluons and infinite quark-antiquark pairs, all virtual. They are created and reabsorbed within the uncertainty principle. So if we now allow also for the QQ bar production, okay, from a radiated gluon, then the result is that your PDF will be increased in this low X region, okay? So higher order processes, such as virtual quark pair production, result in an enhancement of the PDF at low X. The reason why it increases at low X will be clear in the next slide. So the quark content of the proton can be essentially separated into 2 categories. The so-called valence quarks, which is a term that we already used in our course. This corresponds to those quarks that determine the quantum numbers, okay, of the proton and the main properties of the proton. These are what the quarks meant by Gell-Mann and Zweig in the quark model, okay? So UUD for the proton, UDD for the neutron, UDS for the lambda, etc. And then we have the C quarks, which are instead originated by the continuous splitting of virtual gluons into QQ bar pairs. And there are infinite of these into the proton, okay? You have to imagine the proton like, I don't know, extremely complex boiling object, we have inside not only the 3-valence quark, which define the quantum numbers of the proton, but an infinity of gluons and quarks which move inside the proton at the speed of light, essentially. Now, clearly, antiquarks in a baryon can only belong to the C, so from the Q-bar pair, and similarly, quarks in an antibaryon can only belong to the C. Okay? So in a baryon, we have the valence quarks. In the corresponding antibaryon, we have the valence antiquarks. So the valence antiquark for the antiproton are U bar, D bar. Okay. Now, since gluons with large momenta are suppressed by the 1/q² dependence of the propagator, so essentially the gluons are soft, okay? Then the C quarks, which are produced by the gluon splitting, share only a very small fraction of the proton momentum, okay? And so they are dominantly produced at low x. So in fact, the C quark PDFs are mainly concentrated at in the low x region, and the valence PDFs the valence quark PDF are concentrated in the large x. And this is indeed the reason why, okay, when we allow for the quark splitting, so from the C quark inside the proton, we have an enhancement of the PDF in this low x region, okay, because of this. Now, how can we now put all things together? How can we express now the structure functions, which contain, as we said at the beginning, the full information on the structure of the quark in terms of Parton distribution functions? Of course, the two things must be related, okay, within the Parton model. So the Parton model differential cross-section for deep inelastic scattering is given here. And here we can identify two separate contributions. The first one is the one that I showed you before, okay? The one coming from the elementary electron quark elastic scattering, where F1 and F2 indeed are equal to 1, if you remember. So this is the elementary electron quark cross-section. This is essentially almost a pure QAD object, so it can be calculated precisely in QAD plus eventually also correction from perturbative QCD, okay? Because the quark can still radiate a gluon, so you also need to add some perturbative QCD correction here. But anyway, this part here is calculable, okay? And this deals only with the elementary process, electron quark scattering, which is elastic. And then we have the other contribution, okay, which tells you how quarks are distributed inside the proton. Because you are essentially, so the total cross-section is the electron-proton cross-section. So this depends on the fundamental electron quark cross-section, scattering cross-section, times the probability to find your quark with your proper momentum fraction inside the proton. And this is indeed described by the PDFs, which are encoded here, and which are weighted by the square of the fractional electric charge. So this second term here describes the probability to find the quark of any flavor. The sum is over the flavor. Q can be up, down, strange, whatever, with the momentum fraction x. And this is a non-perturbative part. As I was saying before, the PDFs are non-perturbative objects. We have to measure them experimentally. Where this is a perturbative part. Now we can compare these, okay, with the general expression that I gave you half an hour ago, okay, the one in terms of the F1 and F2 structure function. And by just comparing the two, we can infer how we can express the structure functions of the cross-section in terms of the Parton distribution functions. Okay, so for instance, if you just compare this object, this quantity here, F2 divided by x, okay, corresponds to 1 times this guy here. In fact, this is the second equation. Similarly, the F1 that multiplies the square y corresponds to 1/2 of this object here. And this is what we have here. Okay, so by simply comparing these two, we obtain now a relation between the structure functions and the Parton distribution functions. And we can say even more. We can now combine these two relations to obtain also the Callan-Ross relation. So this is a confirmation once more of the fermionic nature of the quarks, being spin 1/2 objects. If you indeed, if you put the two here together, you end up with indeed the Callan-Ross relation. Okay, and so in other words, you can express your F2 as x times the sum of the PDFs weighted by the squared electric charge. So this is a fundamental result, okay? This is the way in the Proton model, the structure functions that encode the structure of the proton inside the cross-section are now described in terms of the Parton distribution function. So in terms of the way partons share the proton momentum inside the proton. Let's make this sum explicit, okay? So let's, for instance, neglect the heavier quark flavors, which essentially they do not contribute to the proton wave function. So let's restrict it just to up and down quarks for the moment. And so when we can now make explicit this sum here, okay, over the two quark flavors that are more relevant, so the up and down. And so we have, and then we have the square electric charge. And of course, let's also allow for the anti-quark, which are produced by the gluon splitting inside, in the QCD vacuum inside the proton. So this is the expression of the F2 structure function for the proton in terms of up and down and anti-up and anti-down Parton distribution functions. Then we can do the same for the neutron, of course, okay? So the distribution is exactly the same, but now the difference is that one has to consider the distribution of up quark into the neutron, of down quark into the neutron, etc. And there is, of course, a smart way to merge the two things, which is by exploiting the isospin symmetry. Okay? We know that from isospin symmetry, the proton is just the counterpart of the neutron. They are just members of the same isospin doublet. And so, based on isospin symmetry, for instance, the distribution of down quark in the neutron corresponds to the distribution of up quark into the proton. And so we can just call UX. Similarly, the distribution of up quark into the neutron corresponds, due to isospin symmetry, to the distribution of down quark into the proton. And this can we just call D. And the same for the anti-quarks. And so based on that, we can now rewrite the F2 structure function for the proton and for the neutron in terms of in both cases now in terms of the proton up and down Parton distribution functions. Let me see where we are. Okay, a few more things. Now, suppose that you are able to measure this structure function, and in fact, people was able to measure this. Okay, one can now integrate this over X. Okay, and you can express this integral in terms of these two contributions, and the similar for the neutron case, where these two contributions, Fu and Fd, are in fact the integral of the quark PDFs weighted by X. So this is the so-called first momentum of the up quark and anti-up quark PDF, and this is the first momentum of the up quark and down quark PDF. So what is the physical meaning now of these two objects? So Fu, which is defined this way, represents the fraction of the proton momentum carried by both up and anti-up quarks. And similarly, Fd represents the fraction of the proton momentum carried by both D and D bar quarks. And these quantities can be obtained directly from measurement of the structure functions. In which way? Let me show you this. So these are the slack results for the F2 structure function for the proton, but it's in a certain Q-square range, okay, as a function of X Bjorken. Okay. So this you can, of course, fit with a certain parameterization, and you can integrate this parameterization in X from 0 to 1. Of course, so the integral corresponds to the area below this curve here. And you obtain a certain value, 0.18. Then you can do a similar approach now with the neutron. Of course, it is a bit more complicated from the experimental point of view, because you cannot create a neutron target. So the best thing to do is to work with a neutron target, which is a bound state of proton and neutron, and then you have to correct your result by the nuclear binding energy between the proton and the neutron. Nonetheless, this is doable. This has been done, and so once more, with the same procedure, one can over-calculate this contribution. Okay. And so let me go back to the slide before, okay? So we have essentially the value of this integral and the value of this integral, okay? The two unknowns are Fu and Fd, okay? But we have two equations. And so we can now invert the two equations. Essentially, it is a matter of solving a system of two simple equations, and one can obtain the value of Fu and Fd, okay? We have two unknown, well, we also have two constraints for measurements. So Fu is 0.36 and Fd is 0.18, it's half of the U. And now one can merge data from different experiments and integrate over all quark flavors. Okay, so let's put everything together. And once you do so, you obtain a value of 0.5. What does it mean? This means that if you account for all quarks flavor, then all the quarks account to only the 50% of the proton momentum. Okay, so they don't share exactly the total proton momentum, but half of it. And of course, the reason is that the remainder 50% is carried by the gluons. The proton is not just made of quarks, but also gluons, which then split into quarks. However, gluons cannot be directly probed in deep inelastic scattering because, of course, they are neutral objects. They don't carry electric charge. Okay, and so they cannot be directly probed in electron-proton scattering. Now, let me remind you that we can split any quark flavor into a valence contribution and a C-quark contribution. Okay, so the valence are those that contribute to the quantum number of the proton, and the C are those that are coming from the gluon splittings. Okay, so we can split a U as a UV plus US, the D PDF as DV DS, etc., and also for the C-quarks. Okay. Now one can assume that all the anti-quark and C-quark partial distribution functions are the same in first approximation, since they all come from the gluon splitting. Okay, so there is no reason to expect, in principle, a different distribution for the anti-up or the anti-down or for etc. Okay, so under this simplifying hypothesis, we can call all of them like SX, where capital S stands for the C-quarks. Okay, and so we can now write down the structure functions, either F1 or F2 or F1, in terms of the valence up quark, valence down quark, and all the C-quarks altogether. Okay, still taking into account the proper weight by the squared electric charge. Now, since the proton consists of two valence up quark and one valence down quark, of course, the PDF UV and VV are constrained by the normalization condition that we have to have two up valence quark in the proton and one down valence quark in the proton, and vice versa for the neutron, of course. Okay, let's make a break. Let's recombine at 12:20. Any questions? Okay. Siete?
Sì, ci siamo.
Ok. Okay. So let's continue. So in the last part of the lesson, we discussed about the Proton model, how to interpret the cross-section in the Proton model, and how to describe the structure function, which enter in the most general Lorentz invariant cross-section, in terms of the Proton distribution function, which are non-perturbative objects that describe the way the quark momentum, the proton momentum is shared by quarks. Okay, and as we will see next time, in general, this can be extended also to the gluons. So one can also have the gluon PDF as well. We describe the way gluons share the proton momentum. Now, I showed also some very old results from SLAC. Okay, but of course, in the next decades, sorry, in the following decades, many DIS experiments have been done in the world in many high energy laboratories, and today we have much more precise knowledge about the proton structure that we will show you now and also next time. So one major advance in understanding of the proton through deep analysis scattering was provided by the measurement. I'm sorry, I forgot to show you something before. Sorry, before that. So, yeah, this was a slide that I had this morning. So you find all in the, if you download now the latest version of the PDF, you find this. Otherwise, yesterday was not there. So back to this. Our assumption was that all the distribution of all the C quark PDF were indeed the same. Okay. So we just call them capital S, because in principle one should not expect big differences because all these guys come from the splitting of gluons. Okay. And this was our assumption. However, okay, this is apparently not the case. So let me show you these results that have been published on Nature, so a high prestigious journal, just 2 months ago. And this shows you the ratio between the D bar divided by U bar PDF as a function of X Bjorken. The yellow results are the ones relevant here. Okay. And what you see here is that the ratio of these two is far away from being a constant, from being 1. Okay, the ratio is well above 1 in a very wide X Bjorken range. So contrary to this naive expectation and naive assumption, nature is more complicated than one would expect. And in fact, it appears that in the proton there are more D bar than U bar quarks. There is a very recent result that need to be understood and, of course, also theoretically. But I think it was important to mention now this. So I was saying before, the major advance in understanding of the proton in deep analysis scattering was done in the years 1991 to 2007 at the HERA machine in Hamburg, in Germany. So HERA was an asymmetric electron-proton collider. So we have 2 rings. In one ring, high-energy protons were circulating with energy of 900 GeV, 800, 900 GeV. And in the opposite way, so in the other ring, electrons was circulating with an energy of 27.5 GeV. In this sense, it is an asymmetric. Not only different particle types in the different beams, but also different energies. Okay. And then there were, you see here a picture of the machine, of the HERA. You see here, this was the proton beam line, this was the electron beam line. And you see here also a picture from the panoramic picture where this machine was located underground in the area of Hamburg in Germany. So there were 4 different experiments. 2 of them were collider experiments, the H1 and Zeus experiment. So indeed, as you can see also from the shape of the detector, it was like a typical collider detector, okay? Symmetric collider detector with cylindrical geometry. And so in the interaction point of these 2 experiments, we had very high energy electron-proton interactions coming from the 2 opposite beams. Then there were also 2 other additional experiments, the ERA B, located here, and the Hermes experiment located there, which were instead fixed target experiments. So in particular, Hermes was using only the electron beam, and it was using a fixed target for the proton, and the opposite at Hera B. Hera B was only using the proton, okay, for fixed target experiments. Now, thanks to Hera experiments, we really expanded our knowledge on the proton in a huge way. You see here the kinematic plane. So here essentially you see Q square as a function of x Bjorken. Consider that both scales are logarithmic. So you see here we have 6 order of magnitudes and another 6 or 7 here. And this is the coverage of the 2 collider experiments, H1 and Zeus, in this kinematic plane. So you see how much information can be encoded here. How wide is this kinematic plane in X and Q square? Another way to see this is that just comparing the slack result that I showed before with the result of Hera. Okay, so you see here how this structure function F2 has been expanded. Okay, in the X up to 10 to the minus 6. Okay, and also in Q square. So Q square ranges from 150 GeV down to 0.1. So we have another 4 order of magnitudes here. Okay, so there is an incredible amount of precise data that have been collected in a wide, very wide kinematic regime at Hera. And this, of course, translates in our information now on the proton structure. Okay, so these are now the combined result by H1 and Zeus, but also some other SLAC and some Fermilab experiment, etc. So F2 as a function of Q square for different values of X. Okay, again, Q square spans like 6 order of magnitudes here. Okay, and also X ranges from 0.00005 up to 0.85. So we have many order of magnitudes in X and Q square. Okay, so let's now look into these results with some more detail. So let's first of all concentrate on the central part of this picture. Okay, the central part of this picture, the results, as you can see, are pretty much flat with respect to Q square. So as a function of Q square. And this is indeed what one would expect based on the Bjorken scaling, okay, that I was mentioning before. So the expectation at the beginning, the founding at the beginning was that the structure functions do not depend on Q square, only mildly. So this is indeed true, but only in this central part of the plot, right? If we now look at the top part and the bottom part, we see that there is a quite strong dependence on Q square. Okay, so F2 is not anymore flat, but it is either rising or decreasing with Q square. In particular, in the region of small x, so from 0.02 downwards, F2 increases with increasing Q square, so the slope is positive here. And in the opposite, at very large x, so beyond 0.4, so 0.65, 75, 85, also 0.4, then the slope is decreasing. So let's now see how can we understand this. So first of all, the observation is that with increasing Q square, the number of partons with high X decreases, while with increasing Q square, the number of partons with low Q square increases. And this is indeed the manifestation of the breaking of the Bjorken scaling. We talk about Bjorken scaling violation. So there is actually a clear Q square dependence of our certain function in opposite regimes. And in particular, at high Q square, so the proton is observed to have a greater fraction of low X quarks. Or in other words, the structure function, as you can see, at high Q square is shifted towards lower value of X. Why? How can we understand this? Well, of course, the value of Q square corresponds to your spatial resolution, as usual, through the Broglie wavelength. So low Q square means that the wavelength of the virtual photon is too large to resolve the spatial substructures. Okay, so you only see few details inside the proton at low Q square. However, at large Q square, okay, this corresponds to a smaller wavelength of the principal photon, then of course your spatial resolution increases and you can inspect a lot of details inside the proton. Where a lot of details means, in a simple way, a larger number of partons. Okay, in this very naive example, you see only 3 here, and you have tens of partons at large Q square. Now, the question is that, if you remember, the X Bjorken is the fraction of the momentum of the proton carried by each quark. So the more quark you have, or you can observe, thanks to the higher Q square, the smaller has to be their fraction, the fraction of momentum carried, because the total, of course, has to be 1. So if you probe your proton at low resolution, so at low Q square, you see only a few quarks, for instance, 3, and so X is of the order of 0.3. But if you probe the proton at much larger spatial resolution, so at much larger Q square, then you see many more partons. And since the sum of X has to be 1, because this has to correspond to the total longitudinal momentum of the proton, then of course each of these partons have to share a much smaller fraction. Okay, so this is the interpretation of the Bjorken scaling violation. Okay, which sounds pretty obvious at the end. Now, by fitting the Q square dependence, so the non-trivial Q square dependence of F2, it is also possible to derive the Q square dependence of the strong coupling constant, alpha strong, the one that we defined in the QCD chapter. And in fact, this was one of the ways to study this running coupling constant. In particular, historically, the observation of the scaling violation in the IS, which was predicted by QCD because of this reasoning here, provided a powerful validation of QCD, and considered one of the first experimental pillars of the theory of strong interactions. Now, the proton PDFs are nowadays extracted from global fits over a wide range of experimental data, which are obtained from very different experiments with very different experimental techniques and very different and complementary kinematic regimes. Okay, so today we have a bunch, really a huge bunch of experimental data on deep Elastic scattering. And not only, so either coming from the scattering of electron proton at collider, like with the Zeus and H1 experiment that was just mentioned at HERA, or electron proton or muon proton scattering at fixed target experiment, like the Hermes or Compass at CERN, or neutrino proton scattering, which is regulated by the weak interaction, proton-proton scattering, and proton-antiproton scattering as well. So you can also, as we will see, probe of course, the proton structure also in hadronic collisions, not only in electron-proton collisions or electron-proton collisions. Now, once put all these things together, okay, and try to perform a global fit, and this is what indeed phenomenologists are doing, one obtain essentially a set of is written here, a set of PDF parameterization, which are, of course, obtained by maximizing the agreement between the parameterization and the experimental data, where the parameterization, of course, has to be QCD inspired, okay, at next to next or even next routing order, okay? So you match your parameterization, which is a QCD inspired parameterization, with your data, which come from very different and complementary experiments and kinematic regime, and at the end, you obtain a set of Parton distribution functions. Okay. In particular, you can obtain a set of Parton distribution function at a specific scale of Q square. For instance, mu square equal 10 GeV, where mu is an arbitrary scale. Okay. Then, of course, you want to evolve these at different scales. For instance, if you want to compare different experiments, low energy experiment with high energy experiment, you have to match the energy scale. So you have to evolve the PDF measured in one case or in the other to the same scale. And this is done through the so-called Diglap equations from the initials of the authors, which are indeed the QCD evolution equation that allows you, once you know your PDF at a certain scale, through this integral differential equation, you can obtain the value of the PDF at any Q squared scale that you like. The main ingredient of these Diglap equations, which are very complicated, I will not enter into these, of course, but let me just say that the main ingredient is this splitting function, PQQ, which describes the probability of a quark to emit a gluon and thence to reducing its momentum by fraction x over y. So this is a pure QCD, okay? A quark emit a gluon, so it reduces its momentum. All this is integrated out, and at the end, you can use this to evolve your Parton distribution function to a different energy scale, or better say, to a different Q² scale. Okay. These are now examples of results. These are only based on H1 and Zeus results, but nonetheless, these are global fits. So you see here the Parton distribution function multiplied by x for graphical reasons as a function of x. So we have the valence up quark distribution as a function of x, the valence down quark distribution as a function of x, and in fact the maxima of this distribution are in the large x region, which is, if you remember, the region of the valence quarks, where the valence quark dominates. On the other hand, and similarly, one can obtain information on the C quark PDFs, okay, which, as you can see, they rise in the low x region. So they share a very small fraction of the proton momentum because they arise from the splitting of soft gluons. And then you can also have the gluon PDF, as I was mentioning before, okay? Now, also look at here, we have a very huge damping factor here, just for graphical reasons, just to have everything in the same graph. Otherwise, this guy would increase like this, like crazy, like almost vertically, okay? So what we can learn from these kind of distributions, the valence quark PDFs are dominant at large x, as I was mentioning before. Then you can see here the up quark valence in the proton is almost double of the one in the down quark, as is expected, because we have two up quarks, one down quark in the proton. The C quark and the gluon distribution are more important at low x, and overall, as you can see, the precision of these results is remarkably high. Okay, there is a part of the uncertainty is due to experimental results, a part is due to the parameterization, a part to the model. So a part is theoretical, a part is experimental uncertainty. Nonetheless, after 50, 60 years of deep Elastic scattering, we have now reached a very precise understanding of the momentum distribution of quarks inside the proton. Okay, any questions? Now, yes?
I was going to ask, what about the flavor itself? I mean, is it because the other quarks are heavier anyway, they would be created in pairs less often, so you don't need to care about them, or?
You're talking about heavy flavors in the
yes.
proton? Yes, okay. Most of them are included in the C part, okay? So SS bar come from the gluon splitting, and with very, very small probability also TC bar might come from the gluon splitting. This is, however, nonetheless not the end of the story, because there are certain theoreticians, very talented theoreticians actually, who are pushing a lot their theory about the possibility of having intrinsic charm into the proton. So essentially, they work out Hartree-Fock wave function of the proton, which also include intrinsic, so not perturbative, but intrinsic contribution from charm. Okay. The theory is pretty clear. The predictions are pretty clear, but up to now, there are no experimental confirmation of this. In particular, it is predicted that this intrinsic charm, so non-perturbative charm in the proton, should contribute at large x. Okay? It has been searched for, but for the moment, there are no evidences. Okay?
Okay, thanks.
Now, so if you look at this picture, it seems that we are done. I mean, everything is understood. We have a very precise determination of the PDF. We can go home, right? No, we can't. Because up to now, we completely neglected the spin degree of freedom, okay? So what we have been discussing today, and also yesterday, was essentially about momentum distribution, right? But quarks and also gluons carry spin. And so we have also to understand how the spin, the proton spin, is shared by its constituent. There is a nice sentence by Jeffy, who is one of the fathers of the Parton model and the IES framework, who said, you think you understand something, now add spin. And in fact, now a lot of problems arise when we want to include also the spin in this description. This is a nice picture of Pauli and Bohr trying to understand what's going on with this spinning. So let's start to attack this part, so the spin dependence. We will start today, we will continue next time. So the Proton distribution function, Q, which in general depends on x and q squared, as we've seen, okay, due to the violation of the Bjorken scaling, can also be denoted as F1. Q can be up, down, strange, okay, as usual. And this is also denoted in a different notation as F1Q, okay? And these are called, indeed, momentum distributions or unpolarized PDFs, because they carry only information about the momentum distribution of the quarks, but nothing about the spin of the quarks, okay? So in this sense, they are unpolarized, or spin independent, better to say. So they describe, as we have seen today, the probability density to find a quark of a flavor Q carrying a fraction x of the nucleon total longitudinal momentum, regardless of its spin orientation. Okay? Now, this unpolarized PDF or momentum PDF, so the one that we just studied, can be actually decomposed as the sum of the quark density with spin aligned with a plus sign or anti-aligned to the spin of the proton. The proton is a fermion, okay, it can be, for instance, spin up or spin down, okay, so you have a direction, a reference direction, and you can infer whether your quarks inside the proton, which are also spin or fermion, have their spin parallel or anti-parallel to that of the proton. Okay, and so in other words, how spin is distributed inside the proton. So the Q PDF we can write, we can call equivalently as F1. Okay, can be indeed given by the sum of these two contributions. Okay, and since you have the sum, you are essentially adding up both quantities. So in a sense, all these quantities spin independent. You are summing up both spin projections. Okay, so Q plus is the PDF of a quark of flavor Q with the spin of the quark aligned to that of the part of the proton, Q minus with the spin anti-aligned, so anti-parallel. And so we can now express our structure function F1, okay, in the usual way, where now we are using F1 instead of Q, but of course it is the same, in terms of the sum of these two contributions, Q plus and Q minus. But how can we measure those? How can we measure separately the Q plus and the Q minus? In order to do that, we need to perform polarized deep inelastic scattering experiments. Okay? And from the practical point of view, you need a longitudinally polarized beam of electrons. This means that when you have a beam of electrons, the spin distribution is not random, but they are all or mostly aligned parallel to their momentum. Okay? Either parallel or anti-parallel. This means that your beam is polarized. So the population of, let's say, parallel and anti-parallel are very different. If they are different, the beam is unpolarized. If they are equal, the beam is unpolarized. And then you also need the longitudinally polarized proton target. Okay? So you need to construct a system which is quite complex that allows you to polarize your proton target, to maintain the polarization during the experiment, and also to swap the polarization, to swap the polarization, because you want to check both polarization states. So these experiments have been done in the past decades, and they are still ongoing. The Hermes experiment that I mentioned before at HERA was one of those. And the COMPASS experiment also at CERN, still working, is one of those. And then there is also another set of experiments in the US, in the JLab laboratory in Virginia. So how it works? Suppose that we start our measurement with the longitudinal spin of the target proton opposite to that of the incoming electron. So we have an electron whose spin is oriented in this way, and a target proton, so this is the electron beam. The target proton whose spin is opposite to that of the electron. Okay? So suppose we arrange our system in this way. Now, the spin orientation of the incoming electron is transferred to the virtual photon. Of course, the electron interacts with the quark or with the proton constituents through the exchange of a virtual photon. And so in the process, if the electron is polarized, also the virtual photon will be polarized in the same direction. There is a spin transfer. Now, due to angular momentum conservation, the virtual photon can only couple two quarks with opposite spin. You see here, for instance, this quark in green, okay, which is opposite to the direction of the spin of the virtual photon, you see? And this is the only way this can happen, because the photon is a vector boson, so it's spin 1. So if you have a spin 1 and you have a minus spin 1/2, you can flip to plus spin 1/2, and angular momentum is conserved. But if you have spin 1 and spin 1/2, you can do nothing. Angular momentum will not be conserved. So let me repeat once again, the angular momentum conservation essentially tells you that the virtual photon can only interact with the quarks with opposite spin. And so with quarks, Bose's spin is parallel to that of the proton. You see, they are both pointing to the left. So if your electron spin is pointing to the right, in your scattering process, you cannot interact with quarks whose spin is pointing to the left, as it is the proton in this configuration. Then what you can do? If you have a smart polarized target system, you can swap the polarization of the proton. So the beam is still polarized in the same way, but now you can polarize the proton in the opposite way, okay? And for the same reason, the photon cannot interact with the quarks which have opposite spin. But in this case, the spin of the quark is opposite to that of the proton. So in the first case, you are measuring the sigma plus minus cross-section, okay? So you are essentially touching the PDF of quarks which have spin parallel to that of the proton. In the other case, you are describing PDF which have the spin opposite, PDF or the quarks which have spin opposite to that of the proton. And this is the way to measure separately the two contributions, Q plus and Q minus. Is that clear? Now, once you measure them, you can do two things. You can sum up them, and so you can reproduce your momentum distribution or unpolarized distribution, or you can take the difference of the two. So if you take the difference of these two cross-sections, you are sensitive to the difference of these two PDFs, okay? Those of quarks with spin aligned to the proton and those with quarks anti-aligned, okay? And we can call these objects, so Q plus minus Q minus, we can call as delta Q. So delta Q is a new genuine PDF, okay, that in analogy to the unpolarized we can call G1 instead of F1, okay, which is given by the difference of these two partial distribution functions, okay? The one describing, let me tell you here the full description. So this object here, so delta Q or G1 if you like, it is called the helicity distribution of the proton. And in a longitudinally polarized nucleon, it describes the probability to find a quark with momentum fraction x and a longitudinal spin parallel to that of the nucleon, minus the probability to find a quark with momentum fraction x and longitudinal spin opposite to that of the nucleon, okay? Plus, minus, minus. Now, this quantity was measured already in the 80s, okay, and everything seemed to be fine in the 80s. So in the very first experiments performed in the late 70s, early 80s, it appeared that the majority of the spin of the proton was indeed carried by quark. But then something completely unexpected happened in 1988, okay. This was done by a new generation experiment, the Emc experiment at CERN, with a much, much higher precision than the previous generation experiment. And the striking result of the Emc experiment was that actually quarks carry only a small fraction of the proton spin, roughly 30% only. Okay, so naively, one would think that the proton is made by quark, the proton is a spin 1/2 object, the spin 1/2 of the proton is made by the sum of the spin 1/2 of the quarks, properly combined. Okay, this idea is wrong. Okay, it is now clear since the Emc experiment that actually quarks carry only a small fraction of the proton spin, only roughly 30%. And this opened the so-called spin crisis. So there was, in a sense, a crisis in the high-energy physics community because it was unexpected. And this crisis essentially triggered a lot of both experimental and theoretical work, trying to understand where is the rest of the spin of the proton. Okay, if it does not come from the spin of the quark, where does it come from? So let's see how can we build up the spin of the proton. The proton is a spin 1/2 object. Okay, so we have a contribution to the proton spin coming from the spin of the quark. So the delta Q Helicity distribution that I just defined before, from the up quark, from the down quark, the valence, and also from the C quark. But clearly, this is not the end of the story, because within the proton, you also have gluons. And gluons also carry spin. So, of course, they can also contribute to the spin of the proton. Still, this is not the end of the story, because within the proton, quarks and the gluons can rotate, and so they can contribute to the proton spin also in terms of orbital angular momentum of both quarks and gluons. So this is the full spin sum rule for the proton. Okay, so we have many contributions. At the beginning, only the first contribution was supposed to be important, but then the EMC experiment revealed that these only contribute 1/3 to the total spin. And so the other two contributions must have to be sizable. Okay, the sum of these must end up to 1/2. So what we know today we know that the spin contribution arising from the quark is only 30% of the proton spin. The spin contribution arising from the gluon, the delta G, is less constrained. Okay, it ranges from 20 to 40% because there are a lot of uncertainty. Only few experiments are sensitive to the delta G. And anyway, the present measurements are only provided in a relatively small X Bjorken range. Okay, and so the rest must be orbital angular momentum of both quarks and gluons. And here I put a question mark, because up to now, we are in 2021, nobody knows how to measure this quantity, how to measure directly the orbital angular momentum of quarks and gluons. The only way to access this quantity is through indirect measurements, okay, in a way that we will somehow touch tomorrow, next week, okay? The message is that there is a large missing part of the proton spin which necessarily has to come from the orbital angular momentum of quark and gluon, but we don't know how to measure this. So this is the spin puzzle, the proton spin puzzle. So we have many contributions, okay? The gluon spin, the quark spin, and then the quark angular momentum and the gluon angular momentum. So to summarize, quarks account only to the 30% of the proton spin. The C quark contribution is poorly known. So this guy here, still poorly constrained from experiments. The gluon also, okay? There are a measurement from the RIC mainly at Brookhaven. But again, the uncertainty is still quite large, okay? And then the big question mark is about the role of the orbital angular momentum. Now, these results, which are not particularly recent, okay, but give you anyway an idea of the status of the delta Q present knowledge, okay? So here you see the delta U plus delta U bar, or the delta UV, okay? You see that the uncertainty is pretty small. So today, after decades of polarized deep Inelastic experiment, we know quite something about the Helicity distribution of valence quarks. However, if you look now at the anti-quarks, okay, which must be C quarks, then the uncertainty is still very large, okay, for the up, the down, and even the strange. So there is still a lot of there's a big need here still to precise experimental data to constrain this distribution here, okay? And what about gluons? The situation is even less constrained for gluons, okay? You see here essentially the integrated gluon Helicity function as a function of X Bjorken. And this blue zone essentially tells you the size of the uncertainty, okay? under different conditions as a function of X Bjorken for the gluon helicity function. Now, this light blue window here, which is still quite sizable, okay, is now after the more recent data from Rick, okay? And the dark blue region here is only a projection to the precision that is expected to be achievable at a future Electron Ion Collider. The Electron Ion Collider, as the word says, is indeed like a HERA, like the HERA synchrotron. It is a collider between electron in one beam and ions in the other beam. This project have been last year, so in 2020, approved by the Department of Energy of the United States, and it has been decided that this machine will be built in the next decades at Brookhaven, at BNL. There is, of course, a huge international effort into this project. It's a huge project. We have to construct a huge machine from scratch, partially existing, but mainly from scratch. You have to construct new detectors. There is a call now for an international call for collaborating to this project. And Ferrara is also involved in this. Okay? There is a group here in Ferrara involved in this Electron Ion Collider project. So this is the future, and likely the Electron Ion Collider will put the last word on this spin puzzle, the Proton spin puzzle. The time scale will be, if things go as expected, like physics run starting in 2030 something, 33, 35. Okay. So it's a good place for a new generation of physics like you. Okay, we can stop here. Do you have questions? Okay, we will continue and complete the journey into the proton structure next week on Wednesday. Let me stop the registration now.